So, good afternoon and welcome to the webinar on projection, extrapolation and cost-benefit analysis. We will have a diverse program on these three topics with various speakers. So let me introduce you to them. My name is Sietse Kaalsvaart. I'm the project manager at TNO and the coordinator of the V4SAFETY project. And I'll do a quick introduction. Second speaker is Maria Pole. Maria, maybe you can say a couple of words yourself.
Yes, welcome. So I'm Maria Pole. I'm the group leader of the Vehicle and Road Safety group at the Fraunhofer IVI in Germany. And we are, of course, also part of the V4SAFETY project involved in the extrapolation and projection.
Next speaker is Henri Chajmowicz. Henri.
Good afternoon. I'm Henri Chajmowicz, working at Lab France, the joint research body on road safety by Peugeot and Renault, and I lead the work package 6 in the project V4SAFETY.
And that's the work package on use cases and including these three topics that we present today.
Exactly.
Yeah. Next speaker is Uri Sander.
Yes, hello everybody. My name is Uri Sander. I'm a senior technical leader for data and analytics at Volvo Cars. And Volvo Cars has been running simulations and work package 6 and also considering extrapolation in space.
Thank you. Next speaker is Wim Wijnen.
Yes, good afternoon, everybody. I am an independent researcher and consultant. I have my own company called W2 Economics. I'm an economist and my work mainly concentrates on economic analysis of road safety. I'm one of the partners in the V4SAFETY project and I'm mainly involved in the cost-benefit analysis.
Thank you, Wim. So then let's quickly introduce you to the project, just to give you the context of the work that will be presented later. So it's a Horizon Europe project running for 3 years and ending this month. We look at prospective safety assessment. So that means what would be the safety improvement if I would introduce this or that safety measure. And we do that through simulation. So our goal is to really work on a transparent and simulation-based framework for this safety assessment. And we look at safety measures in vehicle, infrastructural, or behavioral. So it can then be quite a diverse set of safety measures. And in the end, we want to increase the reliability and acceptance of simulation in safety studies. And in the long term, also maybe for type approval. If we look at the objectives, so what we want to or have delivered is a predictive assessment framework for road safety. This includes behavior models, human behavior, but also driver models for automated driving. What is very important is a baseline generation method, which means what do I compare my new safety measure to? What is the baseline situation? What data do I use for that? The next thing is modeling the safety measures. So this is modeling the technical behavior of the safety measure and how successful it is in improving safety. This has all been demonstrated with use cases, over 10 of them. And we also developed a methodology for projection over time and extrapolation across regions, which will be on the agenda today. We have strong link to standardization. One is in the ISO working group, and 2 is in the network called Peers, which is on prospective safety assessment, and is a volunteer network of partners, open network, preparing standardization work. The partners in V4SAFETY are the following. It's 17 of them, which is a nice count. It's actually, yeah. So it's a sizable project, which makes it very effective in its in collaboration. This is the 4th webinar for V4SAFETY. So we have done quite a few already on the framework, on the baseline approaches, and on the simulation structure. So today is projection and extrapolation and cost-benefit analysis. And on Thursday, there will be one on the human models. So this is the moment where I hand over to Maria, and she will start the presentation on projection and extrapolation. As a matter of order, we will have Q&A sections at several points in the webinar. You can already enter your questions using the Q&A button in the menu bar of Teams.
Okay, so I would hand over now or take over. Yes. Okay, so then welcome again from my side. I'm gonna lead you through the, let's say, theoretical part of this webinar on the projection extrapolation. So I will always give you the theoretical background on our framework, and then we'll hand over to the partners so that they can give you an in detail and in-depth explanation of what we have done in V4SAFETY concerning the extrapolation and projection. Okay, first of all, let us come to the difference between both. So if we are talking about extrapolation, what we mean is, in fact, that we are doing an extrapolation in space, meaning that we have our simulation or simulation results we are doing, and then we try to predict how those values would look like if we try to adapt those to another spatial content. Meaning that there could be differences between our simulation area and our implementation area, where we have to take care of some possible biases like demography changes, urbanization differences, and so on, which we have to take into account when we would try to make an assumption on how those simulation results would look like in another spatial context. The other thing is projection in time. And there we use our simulation results and we try to make some future assumptions, and not assumptions, but future outcomes based on the current and past data we used within the simulation to make some kind of informed predictions about trends in the behaviors, the conditions, or the effectiveness of, let's say, automatic driving functions. Okay, I would like to start with the extrapolation in space. So why do we need those kind of extrapolation in space? So what we have when we have our simulation results is that we have some kind of results of the accident frequency or maybe the severity reductions, but under other specific regional characteristics, this could look completely differently. So maybe because there are other vehicle standards, for instance. So we have some kind of effects of the driving functions that may be different in other regional contexts. And the results in the region which we made the simulations on may be not similar to our transferred region. So we need to do an extrapolation in space. Within V4SAFETY, we have the theoretical framework, and don't get too fussed about it right now. I'm going to go step by step through all those frames and explain you what we are doing in the theoretical framework for the extrapolation in space. So where we start is we have the sampling region where we collected our simulation data on simulation results. And we have our target region to which we want to extrapolate our results. So what we have to do is in both regions, we have to select databases which can be used for the simulation or representative statistics of databases in our target region. In the first step, we have a look if possibly in our sampling region where we took our simulation data from, there is a bias. This means that it could be that within the simulation area, we have a completely different urbanization, so that our results and thereby our accidents we had a look at are maybe completely different in the distribution. If this is the case, then we have to look at the data and we have to identify common characteristics which we find in our sampling region as well as in our target region. And if this can be matched together, then we can create groups in which we take out the relevant crashes in their frequency so that we know how many accidents of certain kind of components, groups, are in which region, sampling region and target region. And in the next step, we have to compute weighting factors from the sample region so that we can transfer our results from the sampling region to our target region. And thereby, it could be that we have to have a look at certain kind of event settings or intermediate databases so that it might not be completely transferable just for one target region from one sample region to a target region, but maybe we need steps in between to calculate, for instance, these weights. Then the next step, it may be that we have an approach which includes a multi-stage weighting approach. For instance, if we have one regional difference in our sampling region, then it might be that we are going to do a first weighing step from our simulation area or sample area to a subgroup of our regional area where we want to extrapolate the data to. So then we do the weighting to our sub region and then afterwards in the sub region to the target region. And this is what we call the multi-stage weighting approach. Okay, and then finally, if we have both information from the target region and the sampling region, then finally we can calculate the weights and apply them to our sample region to then finally give some results on the possible influence or the possible impact certain kind of influence driving functions could have within our target region. Okay, this is the theoretical framework. So I would now hand over to Uli. He would give you an example application. Okay.
Yes. Okay, then let's see that this works. So I will provide you an example that we have had in the V4SAFETY project. And the evaluation question of this assessment was, what is the percentage of avoided and mitigated crashes in a car turning right, cyclist straight in the same direction scenario? And we look here specifically at intersection. This type of kinematics can for sure also happen on parking spots, but we look specifically at intersection junctions. And then the percentage of avoided and mitigated crashes if an AB is implemented to all cars in Germany and Europe. So the data set where we build the simulations from is from German data. So we had German in-depth data to understand what are the distributions of certain characteristics and what are the correlations between these characteristics, the joint distributions. And so in a first step, we looked into what is effectiveness of such a system in Germany. And what I want to show now to you how we scaled from Germany to Europe. So first, there's not much data one can choose if you want to look into road accident statistics covering the whole of Europe or EU. And what we have chosen here as a data set is the CARE database. It's a community road accident database covering the 27 member states of the European Union. And here we looked specifically into the 2023 data. And just as an information how this data is derived. So in general, there is a so-called CAIDAS project, the Common Accent Data Set, but not all member states follow this data structure, but they can report still on their own police recorded statistics, national statistics. And so that means that there can be a bit of variance in how the variables that the CAIDAS datasets defines, how they are coded. So for some member states, you will not find the corresponding information. And what there is done is called the CARE Plus model. So that means there's an attempt to do a recoding of the corresponding national statistics as much as possible into the CAIDAS data scheme. So this data set CARE is not openly accessible, but in every EU member state, there are representative organizations who can access. And just to give you a point, so if you are interested in understand how the data looks like and maybe want to use it for your analysis, there's the opportunity to contact DG Move, Directorate General for Mobility and Transport, and they may assist if it is relevant research questions that you want to address. So in general, working with the CARE data, therefore, has some challenges, and there could be distinct approaches. You see on the right now a table where you have countries from A to H, and you have certain sets of variable 1 to variable 5. And if you want to do an analysis, you have different opportunities to do an analysis. If you have incomplete data, you can on the one hand say, I will only look at variables that are available in all countries. So then you would select for the rows that are complete. For example, here it would be row C, or for country C and country F. But this may end up that you're not representing all EU member states correctly. The other alternative is to select only the rows which complete sets of variables. That means you have then variable 2 and variable 4 that are available in all countries, but then you may not be able to filter accurately for all the distinct characteristics that you want to address. So in both ways, there's a shortcoming that you may not be representative or lose representativeness in your approach. So therefore, we have chosen another approach, which is a bit of a balance in between. We select relevant variables and countries and also take those variables into consideration where we have missing value for member states, but by imputation, we try to enrich the data so that still a wider data set can be used. So how does it look like? How do we do the filtering of the data? We looked off post-pandemic year 2023, only crashes between cars and bicycles in the CARE database. And then you have a variable that would, in the perfect world, address exactly this scenario that we are interested in the CADA scheme. This is in variable A12, where you can see in the pictogram that at least 2 vehicles turning same road, same direction, and turning right. So exactly the use case that I provided before. But as I mentioned before, we are scaling up from German data, and Germany is one of the countries who is not explicitly following the CADAS scheme. So we cannot select for that specific use case. Instead, we have to set the scope much wider. And we looked instead of all crossing and turning crashes, because what you could see is that you see now 4 rows of pictograms, which those are coded in Germany, but none of them represents that actual use case. But it doesn't mean that Germany only looks at these 4 specific characteristics, but they code all possible turning and crossing scenarios in these 4 categories. So that means we have chosen all crashes that are covering turning and crossing scenarios. Then the next step is we need to select important columns. We know from previous research on biases on dataset that is usually an outcome bias. So we are interested in the severity of the crashes and also most important confounders. These are where crashes have happened. So what we are aiming for is a post-stratification weighting. So as Maria said before, we try to identify clusters, how we can group the European data and the German data, and then compare the cluster sizes or percentages to each other. So what we are using here is we're choosing all the countries. We adding another variable that looks into if the crash has happened at an intersection or not, taking the location into consideration if it was urban-rural motorway. And then we have different severity codings, fatal, serious, and slight. But they're also codings of the severity unknown or even unknown if injured. And as you can see, not all countries code the 3 severity categories. So for example, you can see here France codes unknown severity for serious and slight, and even have some uninjured, and we need to address those. So to look in a first step then into the aggregation, we go country by country, and as said, we are looking at crashes that happen at intersections. So via the label variable here in the table, we can exclude those that do not happen at intersections. And so then the rest can be then aggregated independent of the label when not that junction is excluded. That means we're resulting in a cross-tabulation of the location, motorway, rural, urban, versus the injury outcome. And for Austria, as an example here, we have coded all fatal, serious, and slight injured. And we don't have anyone in injury, unknown injury or unknown if injured. But still from these countries, we can compute what are the percentage or the rates between fatal, serious, and slight. And how we will use these, I will explain later. Next example, we have France. We exclude not at a junction. And here you can see we have the fatals, but we have the unknowns, how or the unknown severity is distributed between serious and slight. And still also we have some injury, unknown if injured. In general, if you look over the overall size, the unknown if injured, they are coming mainly also from the slight injured, because if someone has fatally injured, it is rarely that someone is not sure if someone was injured. The same is valid for serious. So it's more often than compare if the unknown if injured are part of the slight injured. And the numbers here are quite small compared to the overall numbers of the slight injured. So therefore, in most instances, we can not consider, we can exclude those unknown injured because they will only have a very small effect on the overall results, but not so if severity is unknown. So we need to understand how to distinguish between serious and slight injured. And for this, we want to use the shares from other countries where this share is known and which are most similar to the country of interest. For this, we're using agglomerative hierarchical clustering. And you can see here an overview of variables that have been used to build up this hierarchical clustering model to compute the dissimilarity between the EU member states. There are I have not counted them, but at least over 10 of these variables that have been considered here. And for sure, one part is important if you're doing this kind of hierarchical clustering, that numbers that you put in will be normalized. So it takes itself care of how big a country is compared to another country, so to say. So the results of such an agglomerative hierarchical clustering is shown in a dendrogram. And when we looked in here, for example, if we see, we found that the best clustering groups is if we have a cluster size of 8, and there you can see what countries are part of each cluster. And the lower the dissimilarity value, so the earlier they merge on lower level, the more similar the countries to each other.
You
So
need to speed up a bit.
Yeah, so if we look into identifying substitute countries, we can see that we have to impute for Finland, France, Italy, and Estonia. And as you can see, the most similar countries for Finland, we're using island shares, for France, Austrian shares, for Italy, we're using Croatia shares, and Estonia is a bit of a own cluster. So we have no direct substitute, but here the numbers are very small compared to the overall size. So they have not an effect on the overall outcome of depending on how we cluster them. So we have taken the Germany shares because Germany is representing on a lowest cluster level when you're building 3 clusters, the complete cluster in the best way. So now we are at the level that we can aggregate over all the countries and give the summary statistics of the different injury severities versus the location for Europe and for Germany. And we are not interested at the moment here in the specific numbers, but more in the percentages to compute our weights. And from comparison of the German figures to the European figures, we can then compute the weight by a comparison of the European percentages versus the German percentages. So what you see in the table, which says weights from Germany towards Europe, you have numbers that are in between 0.9 and 4.3. If the weight is below 1, that means these weights are downscaled, or these occurrences, urban and slight, are downscaled, whereas if you have a weight which is bigger than 1, for example, motorway and slight injured with 4.3, these are upscaled. These weights are then assigned to each of the cases that we are simulating, and so one case will not anymore represent the case itself, but the corresponding weight, for example, 1.7, if it is a case that has a fatal outcome in a rural environment. Adding this into our results from the simulation, we had close to 1,000 simulation runs, and the crash avoidance rate in Germany was 4.9%, and then we can predict that the treatment of the AB in the EU would be 7.2, and you can also see the confidence intervals here. They're overlapping, so it suggests that this is not statistically significant, the difference. Crash mitigation rate is nearly constant at 8.2%. And there's just a disclaimer to this confidence intervals. We have only computed them describing using the sample size, so they only describe the variance based on the 993 cases, but not maybe if there is any systematic representation issue, for example, from the simulation models. Good. Then I think we are now at the first Q&A.
Yes, so thank you, Uli, for this presentation. And using the Q&A button in the top, you can raise your questions. So Do you have a question to Uli or Maria? I have one for you to start with, Uli. So you showed the dendrogram showing the similarity between European countries. And this is based on over 10 accident statistics parameters. So is that dendrogram now useful for all safety analysis in Europe, or just for the specific right turn that you studied in your use case?
Yeah. So as you can see, it's not only based on, for example, specific statistics on car to cyclist characteristics, but it takes a lot of different characteristics into account. So, this dendrogram is therefore aiming for representing more than just what this specific use case is using.
Meaning that in future projects, we can use the same dendrogram for other use cases to extrapolate to other countries.
Yes, as long as it is as long as it is relevant to those variables that have been chosen for building the dendrogram.
Thank you. I see no other questions in the Q&A, so then I propose that we move on to the next topic to catch up with time a bit. This will be on projection in time. Maria will introduce this.
The mic, sorry. Okay, thank you, Sitze. I'm going to take over again and come now to the second part, which is on the projection in time. With the projection in time, what it's all about is, sorry, some handling. Okay, why do we do this kind of projection in time? If we do our simulations where we implement a certain kind of advanced driver assisting systems within our cars, for instance, then we get a result where we assume that 100% of our cars are implemented with this kind of new feature. But of course, in reality, this is not the state. So it will take some time until we have a car fleet in which, in reality, the whole fleet, or at least almost the whole fleet, will be implemented with a certain kind of system. The result of this is that we have economic costs, of course, to implement those systems or install the systems in the car fleet or in each car. And the social economic benefits of it all will not come to light immediately. So it will take some time, and it will also take some time until we get this, let's say, return of invest on an economic basis, where we equalize our economic costs with the social economic benefits. Another use case where we use this projection time would also be that we can make some assumptions and thereby say when will this return of invest occur in the future, so that we can make a prioritization of which kind of new advanced driver assistance systems we would like to install in the cars because they have the most fastest return of invest. And of course, with all the factors we include with our projection time, it is also possible that we can make an assumption and say something about the robustness of our safety performances of our systems. I will shortly tell you in which kind of part of the framework we are using this is regarded. Okay, again, what we have done is we have a theoretical framework, and again, I will lead you a little bit through this so that you get the idea of what is being done. And afterwards, I will hand over to Henri again, and he will then give you some detailed practical implementation of our approach. Okay. Where we start in the projection in time is that, of course, we have to think about what our target accidents. So it may be, for instance, you have an A/B system. Then, of course, this will only help you in certain kind of accidents. So it may not help you to prevent, let's say, parking. Bad example. The A/B system may not help you, for instance, with single crashes, for instance. So what you have to do is you have to set your target accidents within your sample data, for which you then know at this kind of target accidents this system is supposed to function. Then I've summarized 3 of those boxes. So what you do then is at each year, you have a look what could happen as possible changes over time. This could be like the changes in the penetration rate, so that we have more cars in the car fleet that are installed or equipped with this kind of systems. There may be, and this is where I'm talking about the robustness, it may be that we have changes in the usage rate of the measure. This means that, for instance, if you have an automatic driving, automatic braking systems, that you then say that some people try to shut them off because they notice it's not functioning the way they intended them to be. So you don't have the complete usage rate of the measure, but instead the people shut them off. And this could be because it's not functioning or other kind of influences. And of course, there could be other influences of measures like changes in the design standards of the infrastructure or legal regulations that could also change over time. Then in the next step, you have to think about what these changes of time have an impact on. So this could be either that it has an impact on the accident frequency, so that you have less crashes through the measures, or it could be that you reduce the accident severity. So you have to think on both sides which kind of effects you expect from these kind of changes. Afterwards, you take all those considerations into account and then make an assessment of the measure performance within this year. And then, of course, since it's an extrapolation projection in time, you have to think about if your target year has been reached. And if not, of course, then you start the whole procedure again, integrating the measure with the new changes in the penetration rate, the usage rate, and so on, and go through the next time step. And if you finally reached your target year, then of course you can count the number of casualties that have been prevented in each time slot or each time period, and then sum up how many casualties you may have prevented in each year until your time horizon, and then say which accidents have been prevented. Okay. Then I would hand over to Henri to give a practical example of this framework of the projection in time.
Yep. Let me take control. Can you see? Can you see? I just see the slide in the corner of my screen, but can you see the entirety? Can you? What do you see?
Yes.
Sorry.
We
Yes.
see the
Can
entirety.
you see?
You see the entirety. Perfect. Right. So let me go through an example. So the evaluation question would be, so I will deal with a pedestrian use case, so car going straight versus pedestrian crossing the street, crossing the street outside of any kind of intersection. And the question would be, what can we say of the projection of the performance of the AB for pedestrian system until year 2050 in France? Let's see. So the first thing you have to do, if you have looking at the workflow that Maya just showed, there is a variety of factors that can be taken into account. And the first thing you have to do is identify the current trends in accident, because this is what you will follow at first, and also if identify the different factors that will be that will have an influence of the outcome as time rolls on, because it's easy to get lost. So you have to identify the important effects, and so you have first to analyze the recent situation, the recent past, and look at what you can say. So the first thing, what are the current trends pedestrian victims in this situation, car versus check crossing pedestrian. So you can see that there are three categories of victims: the killed, the inpatient, those are the injured that would spend more than 24 hours at the hospital, and the outpatient is spends less than 24 hours at the hospitals or do not go there at all. So what you can see, so from here, so this is our reference here is 2011, because this is where when our database was collected, and we have looked at what is happening from there, from 2011 until the last known situation. So as you can see, there is a slow, for instance, for the killed, there is a slow drift, and like like a benefit of three kills per year. If we look at the inpatients, so again a positive trend, 70 inpatient benefit each year, and the outpatient the same kind of trend. So this is independent of the. This is not absolutely not the effect of the measure we are looking at, because during this period the uptake of the measure was really either nil or very low. So this is the effect of other things that happen that have an influence of the accident outcome for this use case in France. So, for instance, the regulations lowers lower speed limit or the shift of the modal shift in transport, and people are leaving the cars for electric bicycle, for instance. So this is the combined effect of this is the background for our measure, right? So calculation are done here, but we have to take into account that there is a trend independent of the uptake of our measure. Oops, what's that? That's weird. What happened? Yeah. So this is all. This is if we go into more detail, well, there's an aspect that we wanted to investigate and that was the well, how do I mean the effect of the aging of the population. So we looked at the population of victims, so the pedestrians, by class of age and the category of injury, and also had looked at the causes, so the passenger car drivers who were involved in this kind of accidents, also by class of age and category of injury. So what can we see? And this I just took an example here, but this is a long-standing trend. This is how it goes, how it has been going for at least between 2011 and the present. So what can we see? So the if we look at the victims, the killed, so we see that there is the very old get killed. We look at inpatient, we see that's the very young and the old. And for the outpatient, it is mainly the very young, not so much the very old. So this again is something we have to reflect in the baseline, reweigh it if necessary, but this split into distribution of victim by category of injury and age. And then if we looked at the other way, the causes, doesn't seem to be well, mainly the young adults that are cautious. But we will have a look at how it goes. We'll add an exposure measure to this status to see how it goes exactly. So that's the status, and yeah, also something that we have to check. We will look at the effect of the reduced speed limit in cities. So where do this accident occur? Almost all in cities. That's not a surprise. So this reduction of speed limits, lower speed limits should also have an effect on this on this population. Why did it? Anyway.
A bit hardy.
Sorry? I didn't get it.
I have 7 minutes left.
Oh, all right. Okay, so let's have a look on the let's focus on the elderly, the 60 plus. So what we can see is they are much more represented as victims as their share in the population. There is a big risk for them, for the killed. If we look at the inpatient, well, also a risk, but lesser. And if we look at the inpatient, the outpatient, sorry, well, shares not, well, the risk is not so equivalent to the share in the population, right? Well, this is something we're going to take also into account, that there is a high risk for elderly people to be killed. Let's have a look also. This is also important, that this is the analysis of the cars that are involved in the accidents, and we see that they are mostly old cars. Right, the share in the French market for these old cars 10 plus years is less than 30%. So there is really an issue with old cars. That means also that there will be, I mean, the measure will only have an effect where once even the older car of the fleets are equipped with it. So that's also an important fact. And do we see if you look at the driver, do we see a risk for that older drivers are more involved in this kind of accident than others? Well, as related to the population, we can say no. And that is true for our use case, this J-crossing pedestrian, and that is not true for other use cases such as car turning versus pedestrian, as we know that the elderly have issues with the turning situation, but this is not true for our case. Yeah, some trends we have to take into account also for the baseline, whether so the renewal rate of the fleet. So it's important for the uptake of the measure, and also the state of the new registrations, because new registration would carry the measure after a given date. I'll skip on that. So yeah, just a reminder that we used the German uptake of the measure to extrapolate the French uptake, and the French uptake of the measure is much slower, is half as slow as in Germany, and this is due to the structure of the fleets. When you see the French structure, the French fleet has more small cars that very often are not will be equipped less often than the upper segments, and this is the big difference with Germany. The central segment of Germany is segment C, and in France segment B. So that explains a lot about the fitment. I'll skip on that. No, just again a few words. One of the effects we took into account is that, speaking of the elderly, the EU anticipates a big surge in in the population of the elderly, especially the 75 plus in the years to come. So that would have an effect on the for the same hit. We will have more severe injury because the victims will be older. So this is also an effect we take into account. So again, quickly. So what we did, so Maria spoke of that. So that's a time loop with the 1 year time step from the reference year until the target year. And the idea was to mirror the baseline with all the effects I just spoke of into the various baseline over time. Yeah. Okay. Results. So what we get. So this is the benefits, the annual benefits over the years for the killed, the inpatient and outpatient. There is 2 turning points. The points where the share of the very old will start to be consequent in the population, and also the year in which all the new vehicles will have to carry the measure by law, by regulation. And so this is the main outcome, the main conclusion. So no visible significant benefit until even the 10 plus old vehicles are equipped with ABEP, and that will be right there. And we will well, the ABP will be helping compensating that the population gets older and possibly more severe injury appear on the streets. So the AB will compensate that. Otherwise, it may possibly not be useful. Just a few words on that. Something we didn't take into account is the effect of, you can see the effect of the pandemic there. So the distance traveled by the fleets dramatically dropped, and the fleet stagnated in growth, and the distance traveled dropped. We think that an important hypothesis that was made is that this is an artifact in the fleet, and the growth in the fleet and the distance traveled will recover. So we didn't bother modeling that. So we went straight ahead. And one last effect that could have been taken into account was, there has been discussion. There have been discussion about will electric vehicles be any? Will they cause more accidents between cars and pedestrians? So we compared ICE vehicles and the accidents between pedestrian and ICE vehicles, and the accident between pedestrian and full EV vehicles over 10 years. And what we can say is that for our use case, this is the first line, there is no significant influence or significant difference between EV and ICE. And there are some use cases where we can see a significant difference between EV and the ICE. That, for instance, driving backwards accidents or left turning accidents at intersections, but not the use case we are looking at. So we didn't include the effect of EV introduction to the market in our study. And I believe that's it for me. Did I make up for the time?
You did quite well. Thank you.
Cool. Questions?
Any questions? So if I summarize correctly, you in the original data you already saw that the elderly were overrepresented under the accidents. So that's why you looked specifically at the growth of the number of elderly, right?
Exactly.
Okay.
So they are supposed to be, if you so that's quite impressive, right? They changed the growth. That was this slide. Yeah, this slide.
Yeah.
They're quite impressive. The 70 plus, they're 75 plus. They're really double the proportion in the French population. And if we look at this slide, sorry, here. We can see that the elderly are really at risk of. There is really a risk of being killed. That is really the risk of being killed constant. Not so much injured, but killed.
Yeah.
Right. So when yes.
Mm-hmm. And then you concluded that introducing AB, it will go slowly because there's a large fleet out there that needs to be replaced.
Exactly.
But it will actually compensate for the larger number of elderly.
Yes, exactly. Because indeed, if you look at the trends, the current trends, if there were, I mean, if you have a benefit here on these trends, that's independent of the measure, right? So each victim you gain or you save on this trend disappears from the application field of the AB, right? If there were only, I mean, only these trends and there were no change in the age of the population, then the AB usefulness would be quite reduced, right? But this trend will not. There is no compensation here for more elderly people coming in the scene. So the AB will do that work.
Okay, thanks very much. Henri, you also see that you're really exploring the original data a lot to see for trends in that, and that's what you use in your extrapolation, right?
Exactly.
Projection, I should say.
Projection. Yeah, exactly.
So,
and I mean, effects such as lower speed limit, for instance. There is a variety of effects independent of the measure that are included in that trend.
Yeah.
And I didn't look further in that, but they are independent of the measure, for sure.
So earlier in your analysis, you also showed that young people were overrepresented in the accidents.
Yeah, slightly outpatient. Yeah. No, the injured. Yeah, that's true.
So is that in your projection? Is that in some way reflected, this overrepresentation, or will it be the same?
What happened is that we weighted. I mean, at each time step, the baseline is weighted so as to represent the distribution of age and injury of each year, right? So this is taken into account.
Yeah. Okay. Thank you. Then we move to the next speaker, which is Wim Wijnen. And thank you a lot, Henri and Maria.
Welcome.
Let's go to the next slide. Good. And this is about cost-benefit analysis, because all these safety measures do not come for free, and they will, of course, increase safety and save costs in that way, but they will also cost something in introducing them. Wim knows all about this, so I give the word to Wim.
Yes, thank you, Sietse. I will indeed present the work that we did in V4SAFETY on cost-benefit analysis. Why is it useful or important even to conduct a cost-benefit analysis? Well, CBA, cost-benefit analysis, is aimed at supporting decision-making on road safety investments For example, by choosing between different investment options, which one yields the largest benefits compared to the cost. For example, if you choose between, you need to choose between implementing a new vehicle safety system. You can choose to implement it on the full vehicle fleet, which will cost a lot of money, but also the benefits will be higher. On the other hand, you can choose for implementing it only on new vehicles with lower cost and also lower benefits. With the cost-benefit analysis, you can compare those two options, for example. Cost-benefit analysis is also useful for justifying investments in road safety. Many cost-benefit analyses show that the benefits are mostly higher than the costs. So that helps, for example, to get funding for road safety investments and to have a higher priority setting for road safety. I think that CBA helps to spend resources efficiently. It helps to find the measures that have the highest benefits as compared to the costs. So if you have, for example, a fixed budget, CBA helps to find the measures within the budget that prevent as much as casualties as possible. So in the end, it helps to improve road safety. Therefore, in the V4SAFETY project, we developed a cost-benefit tool, which is aimed at facilitating cost-benefit analysis of road safety measures, mainly vehicle safety systems and infrastructure, but it is more broadly applicable. The tool takes a societal perspective, which means that the cost and benefits for, in principle, all stakeholders in society are taken into account. Concerning the cost, we look at the cost of implementing the measure, and the benefits consist of the avoided cost of road crashes. As you may know, road crashes lead to all kinds of cost. For example, medical costs, loss of productivity, administrative costs, damage to vehicles, etc. So if you prevent crashes and prevent casualties, you also avoid these costs. Well, these costs that you avoid, these are the benefits and the cost-benefit analysis. For the tool, we use case-specific inputs, such as the cost of specific measures and the safety impacts of those measures. And the tool also includes generic inputs, for example, the benefit per prevented casualty. So these are fixed inputs in the tool that are needed to conduct the cost-benefit analysis. The outputs are the balance and the ratio of the benefits and costs. And also we have breakdowns of costs and benefits. But I will show you the tool so you can see what it is and how it works. So this is the tool that we developed. On the left-hand side, we have the inputs for the cost-benefit analysis, and the blue boxes are to be filled in by the user of the tool. And on the right-hand side, we have the results, the cost and the benefit, etc. And I will lead you through this tool. First, you can choose here if we are looking at the cost here. You can choose between cost per vehicle or cost per kilometer road length. So for this illustration, I have inserted the data for the AEB for pedestrians that Harry also presented, which is a vehicle measure. So we're having cost per vehicle. Here we entered the manufacturing cost. There are several types of costs. Development cost, manufacturing cost, annual maintenance cost, for example, for infrastructure. Here we assumed that the cost, the manufacturing costs, which is based on the price of an AV system, that also includes the development cost. So just for simplicity, we have only inserted here the annual manufacturing cost, which we have estimated based on previous research on 64 euros per vehicle. The tool also allows to insert a lower estimate and an upper estimate to be able to conduct a sensitivity analysis. We did this cost-benefit analysis for AEB for the period 2022 to 2050, which is a period of 29 years. And we assume that all new vehicles will be installed with AEB. So that's the investment period in this case is 29 years. Then here we have the annual number of vehicles, new vehicle each year that will be equipped with AEB, which is 1.8 million vehicles each year. Then a very important input for the cost-benefit analysis is the annual safety effect. Here you can choose, depending on the data that you have, between the number of prevented casualties or the number of prevented crashes. Here I choose for the number of casualties because we have data for the casualties, not for the crashes. If the number of prevented casualties is the same each year, then you can fill in here the number of prevented casualties, the number of prevented fatalities, serious injuries, slight injuries, and also, if available, the number of property damage only crashes prevented. In many cases, and also in this use case for AEB, the number of prevented casualties was not the same each year. So then we turn to a non-linear annual change, and we have an additional sheet where we can insert the number of prevented casualties each year. Year one in this case is 2022, and we have data until year 29, which is 2050. We have estimated, based on the analysis that Ari showed, the number of prevented fatalities, which is in the first year 3 up to 116 in the last year. Same for the number of serious injuries, slight injuries, and in this case the number of property damage only crashes prevented was not available. We only have one estimate. The tool allows to insert a lower estimate, a best estimate, and a higher estimate. But for this case, because we did not have these higher and lower estimates, I have inserted one estimate for lower, best, and higher. So they're all the same. So this is the important input for being able to calculate the benefits. These are the number of prevented casualties, so this is the safety impact. The time horizon of the effect is assumed to be 29 years, which is the same as the investment period, 2022-2050. However, in some cases, this time horizon may be larger. For example, if we're talking about infrastructure, suppose that you invest in roundabouts for the next 5 years, then the investment period will be 5 years, but the safety impact will be much larger because the roundabouts will be there for, let's say, 30 years. And also the safety impact will last for this whole time period. So then the time horizon for the safety effect is larger than the investment period. We are using a discount rate, which is a standard practice in cost-benefit analysis, which means that the cost and the benefits have a lower weight if they occur further in the future, because, well, that's a theoretical point in economic literature. People have time preference. They prefer to have benefits and costs rather in now than in the future. So that's what is standards used in cost-benefit analysis. And the European Commission has set standard rates for this. And for high-income countries in Europe, it is 3%. So that's what we use here. So these are the inputs that are needed to be able to use this tool and to conduct a cost-benefit analysis. Then let's move on to the results. These are the amounts in millions of euros. So first we have the cost. which are, as you see, 2.2 billion euros, based on this estimate per vehicle and the number of vehicles and the investment periods. And we have a range here from 1.7 to 2.7 billion euros. The benefits, they are based on the safety impact and the costs that are avoided when you prevent casualties. So the total benefits are estimated at 7 billion euros. And we have breakdowns of these benefits by injury severity, fatal, serious, slight injuries. And I said that we didn't have an estimate for property damage only crashes. Well, the tool allows to make a rough estimate of these benefits based on the assumption that if you prevent fatal, serious, and slight injury crashes, that you also prevent some property damage only crashes. That's an assumption in the tool which may not be valid for all use cases. In some cases, maybe there will be less slight injuries and even more property damage only crashes. So you are not forced to use this assumption, but if you want to include property damage only crashes, then the tool gives the opportunity to do that. And the idea behind that is if you do not include them, then the benefits will be underestimated. But you have to be careful here, it depends on the specific case. Then we have a breakdown of the cost into the cost type that is reduced. So we have a reduction of medical costs, we have a reduction of production loss, a reduction of the human costs, which are the intangible cost of the loss of life and the loss of quality of life. We have we have property damage only reduction and also a reduction in administrative costs. So these together are, as I said, estimated at 7 billion euros. Then the main output of the cost-benefit analysis is the socio-economic return, which says, well, are the benefits larger or lower than the cost? There are two main indicators. The first one is the net present value, which is the benefits minus the cost. So so to speak, the net benefits, which are about 5 billion euros, which is 7 minus about 2 billion euros. We have an interval here, a lower and a higher estimate, because we use lower and upper values for the costs. So the net present value ranges from 5.2 to 4.4 billion euros. Another important indicator, key indicator, is the benefit cost ratio, which shows that the benefits are, in this case, more than 3 times higher than the cost, with a range of 4 to 2.6. So this is a very basic illustration of how this tool works and how you can use it to calculate the benefits and the cost of your road safety measure. As I said, this is an example for a vehicle measure, but it can also be applied to infrastructure measures. In addition to this main sheet, there's an introduction. We have some definitions. And it includes the fixed values, for example, the monetary valuations that we use to be able to calculate the benefits. So I hope this gives you an idea of this tool, how it works, how it can be used for road safety. And if you have any questions, I think we can move on to these questions now.
Thanks, Wim. Are there any questions in the audience? Maybe you can keep the tool on the screen.
Sure.
So earlier you showed that there are some tables in there, like the annual safety impact. So where does this data come from?
Yes, this is a very important input. This data comes from the simulations, in this case simulations for AEB for pedestrians. It's the case that Henri also presented.
Yeah.
So his simulations were the input for the cost-benefit analysis. It does not necessarily to be simulations. You can also get safety impacts from the literature, for example, from meta-analysis or for other sources. So in that sense, the tool is flexible, but it requires, of course, this very important input on the number of prevented casualties.
Yeah. And if I look at these numbers now, I see in year 29 there are more fatal cases, right? Is that correct? Do I read this correctly? 116 versus 3 at the beginning?
That's the benefit. That's the benefit.
It's the
Yes,
benefit.
it's the number.
Avoided.
Prevented casualties.
Exactly, it's the number of prevented casualties,
Yeah.
and then this number increases, but because every year a large number of cars is equipped with AEB, so it's a cumulative effect that we have here.
Yeah. So this directly connects to Henri's projection, estimating how the AEB for pedestrians would contribute to reducing the casualties. Yes. Thank you.
Yes, exactly. Yes, it also illustrates that projection is very important for cost-benefit analysis, because also, as Maria said, the benefits do not occur at the same time as the cost in most cases. So the benefits occur over a longer time horizon. So therefore, it's the time projection is very important for cost-benefit analysis.
Thank you.
In other terms, measures become beneficial over time. And if you don't have the time in an analysis, then you're missing the entire effect, right? And what is also interesting here that the analysis starts in 2022. That's where the system was mandated on all new cars. And if we had been able to have a non-constant increase of vehicle equipped, we could have had a look at what happens before 2022, and then we would certainly have seen that the measure was not beneficial at all.
Yeah.
Because too few casualties prevented and costs, right? That would have been interesting, and that's the next step, right?
Yeah. Okay. So, and then there's another table, the monetary valuation. And so what is the source of these numbers?
This comes from a previous European project called Safety Cube. In that project, we conducted an analysis of the cost of road crashes in about 30 European countries. And we developed standardized values for the cost of a prevented casualty. So, for example, here you can see that the cost of a fatality this was 2015. At that time in Safety Cube time, it was 2.3 million euros. We have used inflation to update it to 2023 prices. So at the moment, the cost of a fatality is about almost 3 million euros. Which includes medical costs, which is not that high, of course, for fatalities, but sometimes they are treated in hospital for a couple of days first. We have production loss, also damage to cars, etc. So all these costs are included in those values. We did a very detailed research in that project, Safety Cube, which we used here as input for the cost-benefit analysis.
So if I download the tool from the V4SAFETY website, I will get all these numbers and I don't have to collect them myself.
Exactly. Yeah, these are the fixed inputs that I talked about. The fixed inputs which do not depend on the case, so you can use them for any case. On the other hand, we have, as I said, we have case-specific inputs like the cost of a measure and the safety impacts. For these inputs, you need to insert the data for the specific case, and so there additional research is needed.
Yeah. Okay, if we now go to the CBA page, then the cost benefits, some of the costs will be with the manufacturer, and other of the best benefits will be with, let's say, society. So is there in any way, is that reflected in some way in the tool? Who gets the benefits, who gets the costs?
No, this is not yet included in the tool. It's a very good point because indeed there's a disbalance. Mostly the cost of improving road safety are paid by car manufacturers or by the consumers if they buy a car, or by road authorities, by public entities, while the benefits are for the road users. This is not reflected in the tool. We just look at the net benefit and the net cost for society, regardless of who bears these costs and benefits. I think that might be a very good next step to also look at who pays for it and who gets the benefits.
Yeah. Okay. Thank you. Are there any other comments from or questions from the audience? And I will briefly wrap up. So first of all, thank you for joining this webinar, and we thank you for attending. We will make the recording available on the website of V4SAFETY. This may take a couple of days. Also what you see on the screen is the names and email addresses of the speakers and the people involved. So if you have questions, you're very welcome to contact them. At the bottom left, you see the website, and also in particular the outputs page, because there you can find all the results of the project. We're in the last 2 weeks of the project now, so there's still new material coming, but there is an immense lot of outputs already there. So I recommend you have a look. And then with that, I want to thank you all for attending, and thanks to the speakers for presenting and preparing all this. And hope to see you soon, possibly in the next webinar on Thursday. Thank you and bye-bye.
Bye-bye.
Bye.
Yes.